Hey there, welcome to chapter 6. All right, we are about almost 2/3 of our way through, and I'm going to try really hard for the next 4 chapters to make sure that the videos don't creep up and get longer. I just get going and then they get too long. So I'm going to try really hard to make this a little shorter. Okay, so again, beginning chapter 6, electronic structure and periodic properties of elements. Some very interesting stuff in here. Okay, so first of all, electromagnetic energy and light. Okay, so here's just some history here. The 17th century, Isaac Newton was working with white light, and white light just means that we have all the colors of light combined together. And then in the 19th century, we had Thomas Young, and he was working on passing light through small slits to create interference patterns. And then we had James Maxwell. And he said, okay, well, wait a minute. Visible light is part of a vast spectrum of electromagnetic waves. Okay, so that means that particles and waves are now connected on a fundamental level that we call the wave-particle duality. So what's a wave? Well, a wave can be a lot of different things, but a wave is an oscillation or periodic movement that can transport energy from one point to another in space. And examples of that might be shaking a rope, dropping a pebble in a pond, expansion of air. So don't really necessarily be thinking, when you think of a wave, you're not necessarily thinking of waves at the ocean. That's kind of a different thing. Than exactly what we're talking about here. It's a little bit like that though. All right, so it's kinetic energy moving through matter while the matter remains in place. Okay, so all waves are characterized by the following. First, we have wavelength, and wavelength has this symbol lambda, and you draw it like this, lambda. It's the distance between two peaks or troughs in a wave. And next you have frequency, and frequency has the symbol nu. It looks like a V, but it's nu. Here, let me write that. First we have lambda. And then here we have this sort of scripty V, and that's the Greek character nu. It's a number of wavelengths that pass a given point in 1 second or a specific period of time that usually we'll deal with 1 second. And then there's the amplitude, 1/2 of the distance between the peaks and the troughs. You draw a line right down the middle, amplitude goes up or down. Okay, so let's take a look at this. Frequency versus wavelength. Okay, so first of all, let's look at what we have here on the left. And we have the distance traveled in a second. And you can see that your lambda 1 in this first one, let me turn on my annotation screen. And the distance here, this lambda 1 in the first one, this is our wavelength. And we have 1, 2, 3 cycles per second, okay? Or 3 hertz, H-E-R-T-Z. Okay, and now our lambda 2 is much shorter. So you can see that when we make a shorter lambda 2, now we have 6 cycles per second. So what you can see is that as lambda or wavelength increases, nu decreases. What that means is that they are inversely proportional. Okay. And then you can look here, you can have the same frequency and you can have the same wavelength, but you can have different amplitudes. We actually won't be discussing amplitude in this chapter. We'll be sticking primarily to frequency and wavelength. Okay, so the unit of frequency, and remember frequency is nu. Okay, it's seconds to the -1, inverse seconds. And these seconds -1 can also be called hertz. So some common multiples of hertz that are often used. So if you're working on it and you need to do some conversions, a megahertz, 1 megahertz is 1 × 10⁶ hertz, and 1 gigahertz is 1 × 10⁹ hertz. Lambda, we'll come over here. Actually, let me see. Yeah. Lambda is generally done in meters. And when we are talking about the speed of light, when we're talking about the visible light spectrum, we will often describe things in nanometers. And the one I like to use for that is that there are 1 × 10⁹ nanometers in 1 meter. And you can also write that backwards, which you'll see later. So electromagnetic waves consist of an electric field oscillating in step with a perpendicular magnetic field, both of which are perpendicular to the direction of travel. And just remember that perpendicular means like this, right? We have these right angles. And it means that if one is going this way, then the other one's going that way. All right. So electromagnetic waves can travel through a vacuum at a constant speed. And we're only going to be looking at these scenarios because once you start taking it out of a vacuum, things get a little funny. This speed is known as the speed of light. And you have 2.998 × 10⁸ meters per second. Okay. Wave speed is equal to wavelength times frequency, or lambda nu. So we can say all electromagnetic radiation in a vacuum travels with this proportion, C equals lambda nu. Okay, so if C equals lambda nu, you can also say that lambda, or wavelength, equals C over nu, and nu equals C over lambda. Okay. So now let's take a look at the electromagnetic spectrum. This one's a little different than the one in your textbook, which I always think is great to use a couple different ones. Then you see them in a couple different ways. I really like this one just because it makes it really simple. And you can see you have everything from gamma rays down here at 10⁻12. And what that means is that gamma rays have a lambda equal to 1 × 10⁻12 meters. And then you have radio waves up here, everywhere from FM to AM radio waves. And so what this means is that AM radio waves have a lambda equal to 1 × 10⁴ meters. And right here, this 4 × 10⁻⁷ and 7 × 10⁻⁷, and again, those are in meters, is our visible light spectrum, all the way from violet up to red. Okay, now it's complicated to talk about things like that. Therefore, usually visible light is listed as being from 400 to 700 nanometers. Planck had to assume that the vibrating atoms he saw required quantized energies. And he wasn't able to explain that, though we have been able to explain that since. Therefore, what we came up with is E is equal to NH nu, where H is now known as Planck's constant, and it's really big. It's 6.626 × 10⁻34 joule seconds. Okay, and we can say, well, that's another way of saying that is E is equal to H nu. Since nu is equal to C over lambda, you can say that E is equal to HC over lambda. And the one that you end up using, it just depends on what you have. If you have nu, if you have frequency, then you'll use this equation. If you don't have frequency, but you have wavelength, then you'll use this equation. And your energy will be in joules. Okay, so let's take a look at a couple here. We have a sodium street light, and it gives off yellow light. It has a wavelength of 589 nanometers. What's the frequency of the light? Okay, so let's take a look here. First of all, here we have 589 nanometers, and that's our lambda. And we're going to be using C equal to 2.998 × 10⁸ meters. It almost looks like a 9. Here, let me make that a little clearer. Oh. 8 meters per second. And we want to know frequency. So we remember that C is equal to lambda nu, which means that nu is equal to lambda oh, whoops, I wrote that. I don't have anything in front of me. Nu is equal to C over lambda. Okay, so it's 2.998 times 10 to the 8th meters per second divided by, now notice that this 589 is in nanometers and I need it to be in meters. So before I can go any farther, what I need to do is I need to convert that, okay? And so we can do that by saying, looking for space, I didn't leave myself any, 589 nanometers times, that's not gonna give me enough room. All right, we'll come down here. 589 nanometers times 1 meter over 1 times 10 to the 9th nanometers. Okay, so we're back to using lots of scientific notation on our calculators. So you should be trying all of these problems with me to make sure that you're really comfortable with the way your calculator does scientific notation. So 589 divided by 1 times 10 to the 9th. And what that will give you is 5.89 times 10 to the -7th meters. Okay, so now I'm going to take that number and I'm going to put that up here. 5.89 times 10 to the -7th meters. And now you can see that your meters will cancel and you'll just end up with that inverse seconds. So 2.998 E8, for me it's in E, for you, whatever you're using for your times 10 to the, divided by 5.89 times 10 to the -7th. And that gives you I can have 3 significant figures here. So 5.09 times 10 to the 14th. And you could either write inverse seconds or you could write hertz. All right, so now let's take a look at the energy associated with these photons, okay? And we had a couple things. We could use A is equal, remember, to HC over lambda. Oh, actually, let me write that in a way that you're used to seeing. E is equal to HC over lambda, or E is equal to H nu. So I could use this 5.89 times 10 to the -7th meters if I wanted to, but since I've calculated nu, I kind of feel like I might as well use it. Okay, so let's, I just need to make sure I'm on the right page for my slides. There we go. All right, so then what we have here is 6.626 times 10 to the -34 joule seconds times 5.09 times 10. All right, times 10 to the 14th inverse seconds, and I'll use that here. And the reason I used it here like this is that you can see the seconds and the inverse seconds cancel out and we're just left with joules. Okay, so I'm gonna pull out my calculator. We have 6.626 times 10 to the -34th times 5.09 times 10 to the 14th. And what you'll end up getting with this is 3.37 times 10 to the -19th joules. So, you know, the amount of energy on a single photon isn't huge. But then the single photon is also very small. So let's take a look at the idea of continuous spectra versus line spectra. Okay, so photons are produced by radiant light of any kind, light bulbs, flames, etc., and they have a range of energies, and thereby they produce a continuous spectrum in which an unbroken series of wavelengths is present. And I have a kind of a picture of that on my next slide. Sort of imagine that rainbow. I mean, this is what happens when we get a scattering. That's why you see a rainbow in the sky, is because the light is hitting the water and the air, in the atmosphere, and it's scattering and it's forming that rainbow. And that's your continuous or your white light that contains all of your colors. But light can also occur as discrete or line spectra. Okay, and that exists at low partial pressure using an electric current or heating it. And so, I'm sorry, exciting a gas, it's a different term, and we have something coming up where we talk about what that excitation means. But we basically take the gas and we take it out of its ground state and pop it into a higher ground state, and that's what creates these line spectra. So each element displays its own characteristic set of lines. You can actually tell an element apart by the lines it produces. And each emission line consists of a single wavelength of light. This implies that the light emitted by a gas consists of a set of discrete energies. And by discrete energies, we don't mean everything, right? The continuous spectrum means everything. It just winds into itself. The discrete ones are going to give bits and pieces. So this is what I mean by that. All right, so what we see here at the top is we see our continuous spectrum right here. It just says 1. I'm not quite sure why, but right here, this is our continuous spectrum of some kind of white light source. And now below, you can see that we have a few others. This one here is sodium. And you can see the line spectrum of sodium has 2 lines and then 2 more lines and 2 lines and 2 lines and 1 line, sorry. And you can see the different colors of this. And what will happen is if you take some sodium gas in a vacuum tube and you turn it on and you put it through a prism, because remember, you only get this continuous spectrum if you put it through a prism. So you put the light coming out of the sodium through a prism, and you'll get these neat looking lines. It's really, really cool to do. And then the next one here we have is hydrogen, and this one's a little bit more spread out. Now look at calcium. Holy cow, calcium has so much in it that you get all of these lines coming out to produce the light that calcium makes. And the same thing with mercury, an amazing number here. So now we have the Bohr model, and the Bohr model talked about how the energies in the electrons of an atom were quantized, and they were specific amounts, and they were described by these quantum numbers. And what the quantum numbers do is they come together to form a possible location, kind of like an address for where you are. It's like if you imagine that you're at home and your address, and it's such and such a state, and such a town, and then a street, and then a house number, and maybe even a room. And all that brings you down to your address, but it's really impossible to know at any given time exactly where you are in your house. I mean, maybe you know, but nobody else necessarily knows if they're not in your house with you, right? They don't know exactly where you are. And the same thing is true of an electron. So the quantum numbers will bring it down from saying, hey, the quantum number is somewhere in Maine, to it's in this house somewhere. Okay, and that's about as much as we can tell you. Okay, so there's a few things in here that brings us to de Broglie's equation. And what de Broglie said was, well, wait a minute, we know that we have particle-like properties for our light, and that's how we see those specific lines. That we know that there's only certain things that can happen, and that means that it's got very specific things that it can be. Okay, but then you also have a wavelength for a particle. So the de Broglie wavelength is a characteristic of particles, not electromagnetic radiation. So electromagnetic radiation has its own wavelengths, but these wavelengths are the idea that quantization can be explained if the electron is considered a circular standing wave instead of just a constant wave, right? Okay, and only integer numbers can fit exactly within the orbit. And we have mass, and we have Planck's constant, and we have not nu, but velocity. Okay, you can take P as momentum, but usually we don't come with that. Now, the important thing here, remember Planck's constant is 6.626 times 10 to the negative 34th joule seconds. And because of this joule, okay, our velocity, V, needs to be in meters per second. So velocity, or similar to speed, but in this case, velocity in meters per second. And our mass, because of the pieces that make up joules, our mass needs to be in kilograms. So remember that we have to convert from grams to kilograms. And remember that there are 1,000 grams in 1 kilogram. Okay, so here, go ahead and read about wave particle duality. And through this, I'm not going to talk about them in here because you guys can read them. We come to the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle is a big one here. And this is one that you definitely need to take away from this. Okay. The Heisenberg uncertainty principle says that it is fundamentally impossible to determine simultaneously and exactly both the momentum and the position of a particle. Okay, so think about position as where your particle is, and think of momentum as velocity and location. Oh, wait, we already talked about location. Think about momentum actually more as velocity. And remember that velocity is speed and direction combined. If you take math and physics, you'll find out how velocity is actually a vector rather than just speed. Usually we use speed and velocity to mean the same thing. Okay, so this is where the electron is and what its velocity is. And we can't know these two things at the same time. Sometimes people will describe the Heisenberg uncertainty principle as where it is and how fast it's going. Just as a way to kind of make it a simple understanding. Okay. All right, where am I at? There we go. Okay. So when we're understanding our quantum theory, and we're only getting into a little bit of this. If you do go on in chemistry and you take more chemistry and you take a couple of years of physics, then you can study quantum mechanics, not physics, a couple years of calculus, sorry. Then you can really study quantum mechanics because you use calculus when you're doing the math for it. But right now we can learn it and we can understand it just based on what we're learning. So electrons and atoms can exist only in discrete energy levels, but not between them. And that's because the energy of an electron in an atom is quantized. And quantized, remember, just means specific quantity or a specific amount, as opposed to anything. The energy can be equal only to certain specific values and can jump from one energy level to another, but it can't transition smoothly. So it's kind of like you might not be able to, you can jump. Okay, let's say that you have, a stream, you have a river, and you have the two sides. Okay, so without getting your feet wet, we'll imagine it's very deep. You can't walk through it simply, but you can jump over it. Okay, and so imagine it a little bit like that. Okay, so that brings us to atomic orbitals. There are 3 quantum numbers used to characterize an orbital. An orbital is a general region in an atom that an electron is most probable to reside. An atomic orbital is distinct from an orbit. It is not the same thing as a planetary orbit. The quantum mechanical model specifies a probability of finding an electron in a 3-dimensional space around the nucleus. And one of the best ways that I've seen to describe the concept of an orbital is to talk about basically if you were in the middle of a field with beehives and you put cameras above the beehives, and let's say you took a picture every minute for a week, you would end up getting a location around the beehives where the bees were most likely to be seen. But you would never know exactly where they were. And sometimes they could be outside of that probability, but not usually. Okay, so let's start talking about our quantum numbers. The principal quantum number, or our first quantum number, is n. Okay, energy levels are labeled with an N value, where N can be 1, 2, 3. 1 is your ground state, usually your lowest energy level. Okay. Generally speaking, the energy of an electron in an atom is greater for larger values of N. And hang on just a minute. Okay, so in just a minute, N is referred to as our principal quantum number or shell number. So it's where you are, the principal quantum number. Okay, so now what I'm going to do is we're actually going to, let me see if I can find it. All right, so now you should be looking at my periodic table, and we're going to put over here, I'm only going to be, actually, before we go back, I'm going to annotate on here a little bit. Okay, so right here, you can say this row is N is equal to 1, N is equal to 2, N is equal to 3, N is equal to 4, 5, 6, and 7. Okay, and that's for what we call our S block here. And then we can come over here and we can say here for, I'll go ahead and change color. Okay, and I'm going to draw a thing right down like this. And we can say the same thing. N is equal to 1, 2, 3, 4, 5, 6, and 7. And this is our P block. Okay, and you'll notice that our N is the same for our S and P. All right, now let's take a look here. Right here, we have our transition metals. Okay, our transition metals, this is our D block, and that'll make more sense in a minute. Now, here we have N is equal to 4, but our D block doesn't start with N equal to 4. Our N block drops down, and we have N is equal to 3, 4, 5, and 6. So you can see how that works. And then down here, this is our F block. And all that will make sense in a minute. You'll see this again. I just like to show it more than once. In our F block, this drops down even farther. So the lanthanoids here go right in here. And your actinoids or actinides go in here. And that drops down even farther. So here N is equal to 4, and here N is equal to 5. So it's the N value, that principal quantum number, describes where you are, basically how many electrons you're putting in, but it's not the same all the way across a row. Okay, here we are back here. That was our principal quantum number. The next one that we have is an angular momentum quantum number, and this is kind of hard. It's a lowercase L, but it's usually drawn kind of with this scripty version of an L, like, you know, cursive, which I know people tend not to learn anymore. L can take on the values 0, 1, 2 to N minus 1. So for an orbital where N is equal to 1, L is equal to 0. When N is equal to 2, L can be 0 and 1. And orbitals with the same value of L form a subshell. Okay, so L equals to 1 is a subshell, and L equal to 0 is a subshell within N is equal to 2. So that's how that works. The angular, oh, wait a minute. Make sure I'm in the right place. Okay. So the angular momentum quantum number, these subshells, are sometimes referred to by their numbers, 0, 1, 2, and 3, but they're also referred to by a letter. So when L is 0, we have S. When L is 1, we have P. When L is 2, we have D orbitals. And when L is 3, we have F orbitals. And now you're probably saying, hey, wait a minute. Remember on the periodic table, I said we had an S block, a P block, a D block, and an F block. And in a minute, you'll see kind of where those are at. But when we have our S orbitals here, there is one S orbital. There are 3 p orbitals, there are 5 d orbitals and 7 f orbitals. And I have this in a picture, but I just want to show you, if I were to sketch a rough image of what these orbitals look like, the s orbital looks a little bit like a sphere. And the p orbital looks a little bit like an infinity symbol. It should be right on top of each other. The d orbital actually looks a little bit like this 3-dimensional clover leaf. Okay. Most of them, some of them don't. And an f orbital, so you can see how we went from 1 to 2 to 4. So if you said, oh, the f orbitals must have 8 loads, you'd be correct. Okay, the primary ones, and then call them the ones in behind. There, hopefully you can see. All right. I always say, oh yes, it's Professor Turmel's drawing abilities. And so you can see how each one gets a little bit more complex. Within these, you can superimpose all of these on top of each other, and you're still going to have places where your probability density is 0. These are called radial nodes. Okay, a node is a place where it is impossible to find an electron. And the number of radial nodes in an orbital is n minus L minus 1. So if n is 1 and L is 0, and then minus 1, then where nodes are none, we have no nodes. But then if L is 2, if n is 2 and L is 0, we have 1 and 2. And so L is 0 for all of these. So these are our s orbitals. And what does this mean, the 0, 1, and 2? This means that you have your s, your 1s, and then you could say that you have a gap. That's supposed to show a gap in between your 2s. Okay. Let me see if I can. There, that sort of shows a node a little bit better. Now it looks like an egg. Green eggs and ham. Okay, and then, so that would be, so this first one is 1s, and then the second one is, well, 2s. See how there's one node in the 2s, and you can see kind of that dead space in there. And then the last one would be 3s. And again, now we have our sphere, and in between we have a gap where we've got nothing. Okay. And that's how we figure out the nodes. And you could do that for any of these, and it shows you how many nodes exist of 0 probability. All right, and this is just a 3-dimensional show that shows 1s here. And then you can see 2s has this little blip and then another one. So 2s, and you can see that space in there where you have a node. And then you have 3s, and in 3s you have that little node and then the bigger node as well. Okay, now we're brought to our third quantum number, and that is the magnetic quantum number, m sub L. Okay, and if an orbital has an angular momentum L not equal to 0, then this orbital can point in different directions. So what do we mean by that? Okay, well, if you have L equal to 0, remember that when L is equal to 0, we have a sphere, right? Now, no matter how you draw a coordinate plane through your sphere, you're a 3-dimensional coordinate plane, that's what this is. It's going to look the same. If you take a ball and move it around in space, it's always going to look exactly the same. But if you have, say, when L is equal to 1, you could have a p orbital that's up and down, or you could have a p orbital that is on its side, and that was That's a terrible p orbital. See? Or you could have one that goes through the plane of the paper. So up and down, side to side, through the plane of the paper, and that could be drawn sort of like this. Okay, so, and that's why you have, remember on the slide before where I said you had 3 p orbitals, okay, and then 5 d orbitals. Well, the way we designate that is with this m sub l value. So m sub l, people hear me say that on video, sometimes they're like, what are you talking about? M sub l means m with a subscript L. So if you can't quite understand what I'm saying, that's what I'm saying, M sub L, M sub L. And so that's what that is. And it goes from negative L to positive L. So for an s orbital, L is equal to 0 and M sub L is just equal to 0. But we have 3 p orbitals for L equal to 1, and then we have negative 1, 0, positive 1. And that's that. Negative L to positive L. And so 5 d orbitals, L is equal to 2. We have negative 2, negative 1, 0, plus 1, plus 2. And so on and so forth. You could keep going. We don't have anything that we isolate in them, but in theory, you could have 9 g orbitals, and L would be equal to 4. And then M sub L would be equal to negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, and 4. Okay, so you could just keep going with this. Who knows? Maybe someday we'll find more elements and we will end up using what is considered right now the hypothetical G block. We're not there yet. Okay, so now what you have here is you have a lovely picture that looks so much better than the picture I was drawing. And it just shows you've got your s orbital up here, and then you have 3 p orbitals, 5 d orbitals, and your 7 f orbitals, and how they get more and more complex as we get more complex in our orbital shapes. Right, now let's take a look. We have orbital relative energies. Okay, well, what does that mean? Well, let's say we're looking at 2s or 3p. So remember, s, p, d, and f are our L values. So in order to tell them apart, we always identify our n, our principal quantum number, and our L value as a letter. So we're always showing both the n value and the letter designation for L. And that tells us pretty close where we're at. Okay, it gives us our shell and our subshell. And I could even write that in. This is shell plus subshell. All right. Now in hydrogen only has 1 electron. And so all of the orbitals in any given level are exactly the same. And we call that degenerate, which probably doesn't make any sense at all. But what it means is that in our ground state, we have energy level equal to 1. Okay, then we have a 1s. And then for 2, we have a 1s and we have 3 2p's. And then for energy level 3, we have s, 3p, and 3d, 5d, sorry. Well, 3d, but there's 5 of them. Okay, and in hydrogen, these are all the same. All the level 2s are the same, all the level 3s are the same. However, that doesn't happen anywhere but hydrogen, because in everything except hydrogen, you have electron-electron interactions. And even in something, say, as small as helium, which only has 2 electrons in the 1s shell, you're still going to have electron interactions that are going to make these subshells exist at different energies. Okay. Now, before we show a few more things, that brings us to our 4th quantum number, and that's the spin quantum number. So the first 3 quantum numbers, n, L and M sub L define the region of space where an electron is most likely to be located. The electron spin is a different kind of a property though. So it doesn't tell you where it is, it describes the intrinsic electron rotation or spinning. And so we talk about that spin as +1/2 or -1/2. More commonly, it's +1/2, -1/2, or like I said, more commonly, it's spin up and spin down. And once we start doing orbital designations, you'll see that we'll make those really quickly where we say, okay, well, in this orbital, we have one that's up and one that's down. So this is a +1/2 and a -1/2, or +1/2, -1/2. Spin up, spin down, up, down. Okay. So in an electron, regardless of the orbital, every orbital can only have +1/2 or -1/2, which means you could only have 2 electrons per orbital. So what does that bring us to? That brings us to the Pauli exclusion principle. If NL, M sub L, and M sub S have to be unique, then no 2 electrons in the same atom can have exactly the same set of all 4 quantum numbers. Electrons can share the same orbital only if they have different M sub S numbers and different spin numbers. Therefore, if 2 electrons are located in the same orbital, they must have opposite spins. Okay, so what does the Pauli exclusion principle mean? Okay, well, yes, literally it means no 2 electrons in the same atom can have exactly the same set of all 4 quantum numbers. And that is its literal designation, but that doesn't make a lot of sense. What it really means is that no 2 objects can occupy the same space at the same time. So I'd love to use this when I'm teaching my teenagers how to drive. And I'm up to my 2nd teenager that we're teaching to drive now. And I say, now dear, you can't go that way because there's a car right there. And according to the Pauli exclusion principle, your car and their car cannot occupy the same space at the same time. So you can remember, that's really what the Pauli exclusion principle is saying. But when it's talking about electrons, then we say that it cannot have the same 4 quantum numbers, which basically means can't be in the same space at the same time. Okay. All right. All right, last slide, then I'm going to take a break because I promised that I was going to make shorter videos from here on out. This is just bringing into play all of the quantum numbers that we could have. Okay, principal quantum number n, allowed values, the angular quantum number, and what this is doing is it's really just bringing everything in that we had talked about before. So what I want to do, for just a moment, is I want to show you a little bit about what this would mean. All right, now if we have hydrogen, hydrogen has 1 electron, right? So it's in energy level 1, which means it's in L0, which means it's in M sub L equal to 0. And M sub S would be +1/2. Next, we have helium. Helium has 2 electrons. It's also in energy level 1 and subshell L0. Okay, and I'm actually going to go ahead and I'm going to put in a little thing. L0 means we're S, and L0 means we're S. And M sub L is going to equal 0 because L is 0, but this M sub S value is going to equal -1/2. All right. Now we go up to our next one, lithium. Lithium has 3 electrons. Okay, and that third electron, now we're in energy level 2. But remember, L can be everything from 0 to n minus 1, which means in this case, L is still 0. And if L is 0, then m sub L is also equal to 0. And our first spin number is plus 1/2. After lithium, we have beryllium. This lecture, also known as How Well Does Jen Have the Periodic Table Memorized? Beryllium, okay, we're in energy level 2, or an L equal to 0, m sub L equal to 0, and m sub S equal to minus 1/2. So you'll see how the first 3 are the same, and then m sub S is different. Okay. After beryllium, now we look at boron. Boron has 5 electrons. So its last one will be energy level 2. Now we've filled our L value, so we're into L equal to 1. And m sub L value, well, remember m sub L can be negative L to positive L, which means we're going to have 3 possible m sub L values. So when L is equal to 1, m sub L can be negative 1, 0, and positive 1. So let's go ahead and we'll start with negative 1, the first one. And then our spin would be positive 1/2. Now, because we can put 2 electrons in each one, that means that the next element, carbon, with 6 electrons is exactly the same. It's still n equal to 2. L is equal to 1. M sub L value equal to negative 1. And now we have our spin going in the other direction, negative 1/2. And this is how you assign the electrons. Now, I've put these in here, but let's take a look and let's say that we're looking specifically at carbon. The first electron in carbon is here. The second electron in carbon is here. The third electron in carbon is here. The fourth electron in carbon is here. The fifth electron in carbon is here. And here we have the 6th electron in carbon. And this is how you identify a different set of 4 quantum numbers for each electron in an element. You could do this all the way up to, I don't know, 109 meitnerium. And you could write out 109 different distinct sets of 4 quantum numbers for each electron, which is really cool. It will not make you do that. I will see you in part 2 in just a few minutes.